Hello everyone, this is Jack Hassamon. Today I will talk about sheet metal forming process. Same as before, we will talk in terms of what, how, why, and what can go wrong. Sheet metal forming process usually starts by shearing or slitting sheet metal roll into small pieces. Then we do punching or blanking. Or we can bend the sheet metal after the first process. And we can go between punching, blanking, and bending. Finally, we smoothen part edges, which is called deburring, and we can clean the part. We will start with shearing process. We have punch and die. Sheet metal is punched. Sheet metal is locked tightly through the sheet holder, which is not shown here. After the punching, our sheet metal now has a hole. The portion that is removed is called slug. You may note that both portions have some rough edges or burrs. If we think of pushing into sheet metal, punching force is rising rapidly in portion number 1. This is called burnish area. This penetration depth is not the entire sheet thickness. Then punching force decreases until the punch goes through the sheet metal. This second portion is called fracture depth. We need to be careful about this operation as it has two different names. If we punch sheet metal and throw away slug, we call this punching operation, as we are punching something out. If the slug is our product, that is, we collect slug to continue with other operation. In this case, we call this operation as blanking process. Shearing operation has other variations also. Parting or slitting is to cut sheet metal into smaller pieces. Perforating is to punch a hole in sheet metal. Notching is to remove part of sheet metal edges to create certain shape. Lancing is to cut sheet metal without removing materials. This is to assist further bending operation that may be done later on. Let's return to blanking process for a moment, shall we? Remember, in blanking, we want to use the slug. If we want the slug to be flat with no burrs, we need to adjust our blanking process. This is called fine blanking. To control material flow, engineers use two important tricks. We use stinger on the upper pad to lock sheet metal plate tightly in place, and we use very small clearance between punch and die, about 1% of sheet thickness, as compared to normal clearance of 2 to 8%. In general, clearance between punch and die is around 2 to 8% of sheet thickness. The smaller the clearance, the better shear edge quality. The thicker the sheet, the larger the clearance, and small holes requires greater clearance than larger holes. Clearance for softer material is less than those for harder ones. We use shaving operations to smoothen shear edges, and shaving and shearing can be combined in one stroke. We can also adjust punch and die shapes to make shearing operation more effective. If we bevel punch or die surface to be at angle at each other, this will reduce force required. The process is more quiet. Engineers can also design punch and die to perform several operations in one stroke. Here in the figure below, a washer is created by material strip. The red portions highlight punch and die for the first operation, punching a hole on the strip. The green portion highlights punch and die for the second operation, blanking the outer circle or washer. Completed washer is shown on the right-hand figure. Progressive die is more advanced than compound dies. Sheet metal coil is fed through the machine, so it is faster than compound dies. Here are basic configurations for stamping press. It is generally designed to allow easy die changing. When we select a stamping press, we need to consider size and shape of workpiece, stroke length, stroke per minute, and maximum punching force. There are a few process parameters we want to pay attention to. We have already talked about shape of punch and die. Punching speed affects width of deformation zone and edge quality. When we increase punch speed, material has less time to react. Deformation zone is smaller, resulting edges are smoother. Lubricating punch or sheet metal will reduce friction, thus punching force required. Clearance between punch and die we have already talked about. Burnish depth increases when we use more ductile sheet metal. Burnish depth also increases when we decrease sheet metal thickness or clearance between punch and die. When clearance increases, material has larger deformation zone. Edges will have more or higher burrs. When material is more ductile, burr height also increases. Maximum punching force can be calculated by the product of material shear strength and sheared area. Material shear strength is estimated by 0.7 times ultimate tensile strength of sheet metal. Shear area is calculated by sheet thickness multiplied by perimeter of shear area. For example, to punch a 25 mm diameter hole through 3.2 mm thick anneal titanium alloy sheet at room temperature, titanium alloy has ultimate tensile strength of 1000 MPa. So we can calculate maximum punching force to be about 0.176 meganewtons. To study how sheet metal is formed, we need to think in slow motion. Once the punch comes into contact with sheet metal is stretched. This elongation continues until necking occurs. Some material, especially low carbon steel, aluminum, has U-point elongation. Once the load reaches U-point, more and more material will start to yield. Portion of yielded material is called Leuders band. This Leuders band is the deformation zone that we want to avoid. We can reduce U-point elongation by co-rolling the sheet, then form the sheet metal. To study how easy sheet metal can be formed, engineers define formability as ability of sheet metal to undergo desired shape change without necking or tearing. To measure this, we put sheet metal in a cupping test. Slowly press until necking or tearing. Formability is represented by depth D just before material failure. The higher value of D, the higher ability to form. More rigorous test for formability is bulge test. Sheet metal blank is marked with grid pattern of circles, then stretched over a punch. We observe how circles on sheet metal is deformed. The direction that circles deform the most is called major strains. The direction perpendicular to major strains is called minor strains. Note that major strains is always positive. Minor strains may be either positive or negative. We test various strain combinations until we find failures, necking, tearing for each material. Then we create forming limit diagrams such as this. The line on this graph represents a boundary for material. Suppose we consider high-strength steel, denoted by red line here. If we operate sheet metal, a combination of major and minor strain below this red line, sheet metal will be formed easily. If we operate above this red line, our sheet metal won't be able to form as planned. We have gone through shearing and forming. Let's look at sheet metal bending. When we bend flat sheet metal, bend radius actually decreases from infinity to some finite number. The outer fiber of sheet metal is in tension, while the inner is in compression. Bending press is generally of the same configuration. The key is the die. Bending dies are designed to bend sheet metal in sequence. Then we have flanging process, which bend edges of sheet metal. Tube bending, which uses form block and chuck or clamp. There are different configurations to support specific needs, such as avoiding wrinkles, bending more than 90 degrees. And we can use different mandrel to support the tube. We can calculate engineering strain from bending. As we bend flat sheet metal, R decreases, R over T decreases, tensile strain at outer fiber increases. At some point, sheet metal may start to crack. Given maximum allowable strain and sheet thickness, we can solve for minimum bend radius R that we can bend for each material. We specify this minimum bend as multiples of sheet thickness. If you can bend sheet metal to the small radius or small end, this material is very bendable. For example, from the table, soft aluminum alloy can be bent 360 degrees. Its bend radius is very close to zero. Hard aluminum alloy can be bent to as low as 6 times sheet thickness. You can improve bendability by heating sheet metal so it is softened. We can improve sheet metal surface roughness. Poor surface roughness is not good for tensile strength. Grain direction within sheet metal is also very important. Grain direction along bending curve is more favorable than grains in other directions. We can calculate maximum bending force assuming no friction by the following equation. Bending force depends on width of die opening W, sheet metal width being bent L, and die type as shown in factor K. For V die, we approximate ultimate tensile strength as 1.3 times yield strength. After we bend sheet metal, material may try to return to its original position. The spring back increases the bend radius. If we define spring back factor as a ratio of original bend radius Ri over final bend radius Rf, with spring back, Rf is always larger than Ri. So spring back factor is always smaller than 1. From the equation and from the graph, we can see that spring back increases means Ri over Rf decreases. To have Ri over Rf decreases, we need Ri over T or Y decreases, or E increases. We can try to compensate for spring back by overbending, or providing support at the bottom. Or we can stretch sheet metal while being bent. This is called stretch bending. Bending at high temperature will minimize spring back also, but this is usually not done in practice. Other variations on sheet metal bending includes roll forming process, spinning process where we use mandrel and a tool or roller to form sheet metal blank. Tube spinning process is to change tube thickness. Deep drawing process is very similar to punching operation, but we do not intend to break sheet metal. Force required for deep drawing is less than punching force. Sometimes blank holder is not used, but sometimes we need special blank holder. For example, we may need to control flow of the blank into die cavity. We can do this by adding draw beads in blank holder. The following equation is to calculate deep drawing force for circular punch. To lock sheet metal properly, blank holder pressure is around 0.7 to 1% of the sum of ultimate tensile strength and yield strength. Too high holder force increases punch force and causes cups to tear. Too low blank holder force leads to wrinkling. Clearance between punch and die has to be slightly greater than sheet metal thickness. Too small or tight tolerance will damage sheet metal. Corner radii of punch and die must be large enough to avoid cracks on the final workpiece, but too large radii will cause wrinkles also. Alright, This is what I would like to say for now. If you have any question, please leave them in our Google Classroom. I will be happy to answer them in our class. Thank you and goodbye.